Buenos días a todos. It's a pleasure to introduce Professor Ulrich Parlitz. Professor Parlitz is Professor of Physics at the Institute of the Dynamics of Complex Systems at Göttingen University in Germany. He's also affiliated with the Max Planck Institute for Dynamics and Self-Organization. The major research topics that Professor Parlitz include time series analysis, data simulation, machine learning, biomedical physics and corridor dynamics, as well as synchronization and control of nonlinear oscillators and networks. His research has resulted already in over 200 publications in theoretical journals and an H factor 48 in the Web of Science. Professor Parlitz is a member of the German Research Foundation and the Scientific Advisory Board of the Conference CBS Dynamics Days Europe. He's also editor of the prestigious journals Physica E, Chaos, and the journals of the Frontiers Union. In this seminar, Professor Parlitz will talk about predicting chaotic dynamics with reservoir computing.
Yeah, muchas gracias. Welcome. Thank you very much for the invitation to this very nice place here. José already mentioned a few things. I'm working at the Max Planck Institute for Dynamics and Self-Organization, and the results I'm going to present today are mainly collaboration with Luke Kellerman, a master's student, and Gerhard Bellecker, who is a PhD student in our institute. Before I go to the topic of reservoir computing, I would like to tell you a bit about our general interest in our group, which is also a motivation for studying, for example, machine learning methods like reservoir computing. In our group, we try to find new ways to terminate chaotic rhythms. And if you go to a medical doctor, he or she may take an ECG, and there may be a normal heartbeat like this, but then there could also be a transition to a signal which is higher frequency, or even a signal which looks more irregular, which is fibrillation. And we study the dynamics of the electrical excitation waves on the heart. Usually this would be movies. Unfortunately, they don't run here today. But this would be something like a plane wave going across the heart, which is induced by the sinus node. This is ordinary operation of the heart. But then there could be so-called spiral wave activations, which leads to this so-called tachycardia signal. And then finally, you can also have a situation where the spiral waves become unstable, and it's a chaotic dynamics on the heart. And this is really a dangerous state, because now the heart is not pumping anymore, and there is no oxygen supply to the brain, and so on. So after 2 or 3 minutes, you will be dead. This is to be terminated immediately, for example, using strong electric shocks. And this is a conventional technology. You know, there are external devices which you can use for internal defibrillator devices, and they work. They excite the whole cardiac system for a moment, and then there's a refractory phase, and afterwards the heart goes back to normal operation. But they are very painful, the high energy damages of the tissue and so on. So that's why people are interested to find new ways using weak electric pulses, for example. And this is what we also do. We do it in experiments. This is an animal heart in Langendorf perfusion system. And this would also be a movie, because this is a pig heart in the state of ventricular fibrillation. And then you would see here all kinds of motion of this electrical excitation, which is made visible by means of so-called fluorescent dyes, which turn electrical excitation into a light emission. And so this way we get interesting spatial temporal chaotic dynamics in simulations, but also in experiments. And the question is, how can you analyze these data? And so this is just a short introduction to give you a bit information of background, why we are also interested in time series analysis and prediction. Now, in general, there are different motivations and tasks for processing temporal data. And the tasks are, of course, forecasting a future value of some given input signal. Or you may do what's sometimes called cross prediction, where you measure one variable, but you want to know the value of another variable that you did not measure at that moment or its future value. And of course, you can also use all these tools for classification of data and also for feedback control and many other applications. And the methods, there are of course plenty methods around. Most of them somehow, at least in the context of nonlinear dynamics, rely on delay embedding, and then you somehow do an approximation of the flow in the reconstructed state space. And there you can use feed-forward networks, nearest neighbors approximations, but also recurrent neural networks, and this brings me to the topic of reservoir computing. Okay, so here's an outline of the talk. Just to give you an idea what I will speak about in the next minutes. First, I want to introduce briefly the chaotic time series we use for testing or demonstrating some methods. Then I will tell you about the basics of reservoir computing. This is quite formal and technical, so if I am too fast, if you have questions, please interrupt me. And after that, I want to show you some recent development where delay values of the input signal and the reservoir state variables are used to improve the performance of the reservoir. And then I will move to the prediction of spatial temporal time series. And there you can use two concepts to get quite quick results. You can use reservoirs running in parallel in space. And we also found that it makes sense to do some dimensionality and reduction in the whole process to improve the results, but you will see. Okay, now, first of all, the data. This is probably familiar to most of you. This is the famous Lorentz 63 model, 3 differential equations producing this chaotic attractor in state space, or this time series here. And actually, you see here different colors. They come from different initial conditions. Trajectories go to the same attractor, but then and show the asymptotic dynamics. It's chaotic, it's non-periodic, it seems to be irregular, but if you look at the structure in state space, of course you see there is some pattern. And this model was named after Edward Lorentz, American mathematician and geologist, who discovered these dynamics during numerical simulations, and he's kind of a father of the chaotic dynamics. He also published a few years later what's sometimes called the Lorentz 96 model. This is a model which consists of a ring of dynamical elements. Each element has a single state variable, xi. So this is, the I is running, and you can use now d of these elements, and you can choose how large d should be. This is periodic boundary conditions, and that's why I call it a ring. And it has a forcing parameter that you can choose. And the nice or interesting thing is that this system produces very high dimensional chaos. If you increase the d, the number of these ring elements, of the size of the ring, then you will see that the so-called Kaplan-York dimension, which is a measure of the attractor dimension in state space, increases linearly with d. And in this way, you can produce very high-dimensional chaotic dynamics as a test case for your method or prediction or whatever you study to do. So these two will be used, and another one I will introduce later. Now, what is reservoir computing? Maybe some of you already use it. For them, it might be a bit boring, but I will try to go at least through the main steps for those who haven't seen it before. So I would say a general description is it's the use of the response of a driven dynamical system, and you use the response of this system, which means the time evolution of this driven system, to predict a target signal. And the maybe most famous example are the so-called echo-state networks, which were introduced in 2001 approximately by Herbert Jäger. And the idea is illustrated here. We have here some input time series, So whenever I use these brackets here with an n, I mean discrete time, and this is a time series, you use it to drive the dynamical elements of some network, a recurrent network, and then you use the state variables of this network, which are given by R, R1 to RNS, and rest is the number of nodes, of course. And you do a linear superposition, for example, where these weights are the parameters you have to determine, and this linear superposition provides the output and the target signal, or the approximation of the target signal. Now, in mathematical terms, you write this dynamical equation, and you see here a lot of things. First of all, we start here with the state of the reservoir at time n+1. This is what we want to compute, of course. And it's a function of the state at time n, and also of the input at time n. And so let's discuss the ingredients here. Here you see, this is a coupling matrix, which describes the network. It's typically a random matrix, and you can normalize it such that it has a spectral radius of 1. Then there is another matrix, another random matrix, which provides the input. So this input goes to the nodes of the network, and this is also formally described by some matrix. There is a constant bias, which is important for breaking some internal symmetry of the system. And then there are more parameters. Of course. So this is computed, and this Q here, this stands for a nonlinear activation function of each of these elements, typically some sigmoid function. And then there are other parameters. For example, this alpha here, this is the so-called leaking rate, which describes how stiff the system is or how quickly it responds to the external dynamics or the external input. Then we have here a parameter nu in front of this coupling matrix, and this can be used to control the spectral radius of the product of the real coupling matrix, which is really acting on the reservoir state. And this sigma here controls the input strength, because this is the input term here, and if you increase the sigma, then there's more impact of the input on the dynamics. And these are hyperparameters you have to choose carefully. And now the output, this quantity here, is, as I told you already, obtained by a linear superposition of the state variables of the network. And this has to be computed. It's basically a least squares problem. I will go into more detail in a moment. And so this makes it, in a sense, a simple task, because to compute these weights, these are the only unknown quantities, you just have to compute, have to solve the least squares problem. And this is something which can be done very quickly, and it's not so difficult on the computer. But all this works only if you have chosen all these parameters here in a good way. So the choice of these hyperparameters has a strong impact on the results. And this means, in principle, you have to repeat this learning part, I mean, this computing these weights, again and again for different combinations of hyperparameters to see how these hyperparameters to optimize, basically, using a grid search. You can also use a gradient descent method, but most people use grid search because the error landscape is sometimes also quite complicated. So, and this makes it expensive, the whole method. So if you read that reservoir computing is cheap, yes, but if you really want to get good results, which are competitive compared to other machine learning methods, you have to do this optimization, and that costs time. Okay, now So this was the ecostate network, which is maybe familiar to some of you. I want to go back to the more general description, which I mentioned at the beginning. So there is an input signal, but now I use continuous time, for example, which is n n-dimensional. This is nonsense here, misprint, but anyway. This should be also discrete, sorry. And so this F stands here for the dynamical system which is driven. In the previous slide it was the ecostate network, but it can be any dynamical system. It has a state, and this is the state of the reservoir system, which is then used for generating the output and for approximating the target signal. You can do the same with continuous time. Here we know the continuous time version. And then, of course, you have here a differential equation, which is driven by the input signal. But it's basically the same story. And now the output is the output of the reservoir, the state of the reservoir, the input signal, because you know it, you can use it, and then typically the constant. So you combine these quantities into something which is sometimes called the extended state vector. This is this x here. And this is then used to provide the output. If you, for example, do again a linear superposition, you would multiply it by some matrix with unknown parameters which have to be determined during the training phase. You can also use here quadratic terms and higher order polynomials, for example, but I don't want to go into these details here. In any case, you would like to use a linear superposition of some nonlinear basis functions, because then the solution of the problem is just solving the least squares problem. The point is, many physical systems can actually act as dynamical reservoirs. So this F doesn't have to be a recurrent network. It can also be a ring laser system. It can be, there are many systems, not all, we'll come back to this point, but in principle you can use, at least you can try to use any dynamical system you have, or you have also the hardware to set up such a framework. Now the training, I mentioned it already, basically means that you have to compute these weights of the linear superposition, and this means we form this extended state vector of the values we know. Then we have some target values, something we want to predict, for example, a future value or some other variable. This is here the vector m, a y, at different times, for example, and this would be time again, discrete time. So if we would have a perfect match, then of course these the extended state vectors multiplied with the parameters would provide exactly the target quantity we are interested in. And so these are some matrices to make the whole computation easier, or to summarize the terms. And you can have more data points and equations, or the opposite. In both cases, it turns out it's good to consider such a optimization problem, where you also have here a regularization part. In this case, minimizing the squares of the parameters you want to determine, the elements of this matrix. And this is standard form of regularization of rich regression with some additional parameter beta that you also have to choose. It's another hyperparameter of the whole approach. And you can solve this, probably you know this from other lectures or your own work, in this way. You need here the transpose, and this is an analytic solution of this optimization problem. And you can also compute the solution using singular value decomposition of this matrix X. So to remind you, the matrix X contains all the information you have, the response of the reservoir, the input signal, and some constant. And then you can compute the desired quantity in these weights for the linear superposition using the inverse matrices of the singular value decomposition, which can be computed by transposition. And on the diagonal matrix here has to be a bit careful, because some of the singular values can be 0 or close to 0, and then you have to take care of this by using here this visualization parameter. Now this is a standard approach. You can also use Moore-Penrose inverse for this operation, for the computation of the output weights. And in this case, you can again use singular value decomposition to formulate the solution. And in this case, you have here a diagonal matrix E, which is given by this term, where you have some threshold value epsilon, and if the inverse, if the singular values are too small below this threshold value, then you do not use the inverse, because that would be a very, very large number, but you replace it with 0. And here in this diagram, you see the different way how the diagonal elements of these two matrices would depend on the singular values. You can look up these things in the publication I will mention at the end of the talk if you're interested in more details. So the main message is you can solve, you can compute the weights you need for formulating the output by using operations from linear algebra, singular value decomposition, and so on. And it's very fast and it's not too difficult. Actually, you could of course also use A1 optimization and other optimization approaches for computing the output, but I will not go into these details. So the main message here is, yes, computation of the parameters you want to compute is doable. Good. Now you have computed the output weights. Now you want to use your reservoir computer, and you can use it, for example, for a single-step prediction. So you predict as output of the reservoir the future value of your input signal for some time period t, capital T. This is for discrete time, or this is for continuous time. You can also do it for discrete time, of course. Now, this single-step prediction can be used, for example, also in a control loop to compensate latency in the control, or as an early warning system that some values may change very soon, very strongly, to predict upcoming extreme events, for example. So this is a useful application, I think. You can evaluate this by a normalized root mean squares error, where you compute here the differences between the target signals y and the output of the reservoir squared, and you normalize it by a standard deviation of the signal, the target signal. And we'll use this error measure also in the future in the next slides. Now, you can also go one step further, and you can do feedback. So you use the output of the reservoir, for example, the future value of the input, and feed it back to the input of the reservoir. You close the feedback loop, and in this way you get an iterative prediction. And so the reservoir is going step by step into the future, and after some steps, you know then, the future evolution of your input. And so again, you train the reservoir in a way that its output, E at time n, equals, if possible, or approximates the future value of the input. And then you close the loop. So this is again the general description of the reservoir from state at time n to state at time n plus 1. It depends on the future value of the input, but you have predicted the future value of the input in the previous step, so you can substitute it here. And if you do this, then you end up with a situation where the future value of the reservoir system is given by the current state of the reservoir system, and this function Gn contains the approximation here with the superposition. And this is now an autonomous system. Only R appears here on the right-hand side, no U anymore. And this runs for some time, and after n time steps, for example, you have a prediction of your input signal n time steps ahead. And there's of course something you have to expect. If you have a periodic time series, you have sensitive dependence on initial conditions. So the predicted time series will deviate from the true evolution, more or less exponentially. And this is one thing, but it could be even worse. The predicted time series can really go to a different attractor, can show a different asymptotic behavior. But let's assume your input time series was a current attractor, and then you do all these things, and then you run this iterative prediction, and you end up on a periodic attractor. This could happen due to the inaccuracy of the prediction, which is unavoidable. And in this case, we would say the climate is not preserved. So the word climate is used here because many approaches in machine learning have close relations to weather forecasting or have been used there for the first time. So the climate means here that you are no longer on the same attractor. You are on a different attractor, so you get a different climate zone. And so sometimes if you want to evaluate long-term dynamics, it's not so important to see whether your reservoir computer is making precise predictions for the next steps, but you just want to make sure that it reproduces the climate of the source of the dynamical system where the input signal comes from. And this is a different way to evaluate the dynamics of the reservoir computer. Another aspect which you should be aware of, in particular if you read publications on this topic, full state knowledge versus partial state knowledge. So what do I mean? Full state knowledge means if I have a dynamical system which was producing my time series, and if I know all state variables, or I can measure all the state variables of the system which produced the time series. So to make an example, let's assume my time series was generated by the famous Lorentz system. If I can observe or measure all three variables, x, y, z, then I have full state knowledge of the system which produces the data. Good. But often in practice, of course, you cannot observe or measure all the state variables. Sometimes you even don't know which state variables you would have to use. And what you have is typically something like a univariate time series. Let's say, for example, only the x of this Lorentz system. And in this case, this is what we call partial state knowledge. In this case, you need something which is one could call at least some state reconstruction approach, maybe implicitly in the dynamics, as we will see in a moment. But to come back to my remark, if you look at the literature on reservoir computing and look what the people are using for demonstrating the algorithm or the performance, very often they use all the state variables. In a few papers consider only univariate time series, and this is a big difference. I will show you in a moment. One has to be aware of. Okay, so here's an example, where we assume that we have full state knowledge, and where we do a prediction, and an iterative prediction. And the prediction starts with, this is the time axis, these are the three variables of the Lorentz system, or their predicted values. The prediction starts here, so from here on, where the dashed line is shown on the left, the reservoir system runs as an autonomous system, and it reproduces the true evolution for quite some time. That's why we see here only green. But then, after about 8 so-called Lyapunov times, I will tell you in a moment what this is, you see deviations. And then the blue and the green, which correspond to the true evolution and the predicted evolution, deviate from each other. They both show typical Lorentz behavior, so this climate seems to be preserved, but of course, trajectories diverge. And so this is 8 Lyapunov times. Lyapunov time is the Lyapunov time is the inverse of the largest Lyapunov exponent. So you may know Lyapunov exponents characterize the exponential divergence of chaotic trajectories. The larger the Lyapunov exponent, the more quickly trajectories diverge. And that's why the inverse of the Lyapunov exponent, the largest, is a measure yeah, for predictability horizon. And and used as a quantity to compare the performance of any prediction method with respect to the dynamics of the data of the system which generated the time series. Okay, now here is the same thing, but now we have used only the Y component of the Lorentz system. This is partial state knowledge. And you see here the same. Here we start iterative prediction, but then already after 5 times, we see significant deviation. Actually, the deviation is also shown here in red. And then the two systems show different behavior. So partial state knowledge, as one might expect, makes it more difficult to predict future evolution. And the valid time is in these cases determined in the following way. You look at the observable Y here, and then when the error crosses some threshold value and becomes larger, then you stop, and that's the valid time of your prediction. Now, a few remarks also on so-called memory of reservoir system, in particular echo-state networks. Here's again the dynamical equation of the reservoir system. I showed you in the beginning with these matrices describing the network and so on. And there are this leaking rate. This was the parameter here, which controls how quickly the state of the reservoir system is changing in time. And then there was this inner coupling strength, mu. And if you would set both of them to 0, then you end up with this evolution here, with this equation. And this has no memory. No memory in the sense there is no Rn here on the right-hand side. So there is no dependence on the previous state of the reservoir. It's only the input signal and then the future value of the reservoir, but no input. And therefore, this has no memory. And some people also study this configuration. And therefore, I want to show also a few results on that. Now, actually, this is shown here. Now, the title is Reservoir Memory Increases Prediction Performance Only for Partial State Knowledge. So this is a message we want to decode now. So we will consider systems with memory and systems without memory. Without memory was this simplified case I showed you on the previous slide. And then we consider full state knowledge versus partial state knowledge. And we do it for the Lorentz 63 and the Lorentz 96. So I know it's a bit confusing maybe, but maybe we go through it step by step. So let's start with the Lorentz 63. The left figure shows we have full state knowledge. We increase here the size of the network, of the reservoir, the number of nodes, make it larger, more complex. And what we see is the valid time, the time we can do prediction, also increases, of course. The more nodes you have, the better the reservoir works, the better you can predict. Everything is fine. And you see also there is no big difference between orange and blue. So with memory or without memory makes no big difference. This is if you have the full state knowledge. If you have an input all the 3 state variables of the Lorentz system. If you have only one, let's say Y, for example, the situation is different. Now, if you don't have memory, it will not work at all. Because you only have this scalar value, and you try to predict something from a scalar value. You want to predict a 3-dimensional vector from a scalar value, and that fails. If you have memory, then you see, again, an increase, because then due to the memory, the reservoir does something like a state space reconstruction, like delay embedding, because it's using previous values and so on. And the same is, of course, happening if you use more complex systems like the Lorentz 96, same situation. Full state knowledge, no big difference, increase, great. Partial, you need you need larger networks here. So that's why I say one has really to look very carefully what is used, all state variables or partial, and then you can also consider these cases whether it's useful or not. Because I mean, there have been publications where people say, well, I don't need this memory here. Without memory, it's fine. But they considered the situation of full state knowledge. Yeah, then it works. But if you go to the other case, it doesn't work. So one has to be very careful. Anyway, now comes an important topic. Why all this machinery or reservoir computing is working at all, or which conditions have to be fulfilled. And this is the so-called echo state property. The point is, you drive a dynamical system, you get an output, you use it for prediction, okay. And then, of course, you have to make sure that this response of the system is reproducible. If you drive it by the same input signal, but the reservoir starts from a different internal initial condition, you want at least asymptotically the same response, because the response should depend only on the input signal, the data, not on something which is going on inside in the reservoir initial conditions, for example. So that's why you need unique response and reproducible response, and which should be independent of the initial state of the reservoir. Now, formally, this can be written that for all input signal sequences from a compact set, and for any pair of initial conditions of the reservoir system, this condition should hold. The two states should converge asymptotically to the same dynamic set. The difference goes to zero. And so this means asymptotically the reservoir forgets its own initial conditions. And if this is the case, then the output of the reservoir, Rn, the state, is a function of the semi-infinite input sequence, and this is called the echo state function. Now, those of you who know a bit about nonlinear dynamics may say, wait a minute, I know this sounds like generalized synchronization. And basically, it is almost the same. I wouldn't say it's exactly the same, I would come to this point, but it's basically the same. So if the input signal is from a dynamical system, which is maybe in a general application of reservoir computing not the case, but if the input signal really comes from a dynamical system, then of course you have the situation, there is a system producing the input, and the reservoir, there's a unidirectional coupling. So it's the situation where people have studied generalized synchronization. And this means, generalized synchronization means that the state of the response system, which is our reservoir, is asymptotically, for a long time, a function of the state of the driving system. So again, the state of the reservoir is asymptotically, for t to infinity, some function psi of the state of the driving system. And this means that each node, if you think about, again, these echo state networks, each state variable of the reservoir is asymptotically some function, Ci, of the state of the driving system. And you can interpret now the whole operation of linear superposition and so on, that you just use these functions and do a superposition. So you can consider them as nonlinear basis functions, which are generated by the dynamics. And yeah, this is what I said already. So, and that's why I said in the beginning, many dynamical systems can be used. You only have to make sure that you get this synchronization by suitable coupling, for example. But I would say it's not sufficient to have generalized synchronization. You also have to make sure that there is only a single asymptotic attractor. And then there's another topic I will not address today. If you look at generalized synchronization, there is a distinction between weak and strong generalized synchronization. And if you want to have good results for reservoir computing, you should go to a range of so-called strong generalized synchronization. Because I found, I'm working with Michi Suikani from Japan, and we are currently studying this. And many people say reservoir computing works at the edge of chaos best. This is something we do not agree, but I will not go into details here. But it seems to be that it's important to be at the edge between weak and strong synchronization. But that's another topic maybe we can discuss later. Okay, now I want to come to my second. This was the overview of reservoir computing in a nutshell. There are many aspects I didn't explain here, but we don't have so much time. Now the idea to make it better. For example, by incorporating so-called delay flaggers. And I will show you this first in a simple example. So I said the reservoirs nodes provide asymptotically nonlinear functions of the input signal, which are used as a kind of basis functions. Okay, now how can we improve the performance? We can increase the number of basis functions, which means practically we increase the dimension of the reservoir system. More nodes, more basis functions. And then we superimpose them, and then we find, well, it works better. Great. But there's another way to do it. You can use not only the states of the reservoir at time n or t, but you can also use previous values of the reservoir states and also of the input. And formally, these, if you do this, you get additional basis functions because you can write the relation of the, maybe it's shown here. If you look, for example, at the reservoir state at time t minus some tau. And you can formally say, okay, this is the psi, which comes from the generalized synchronization. And then this is the state of the driving system, also at previous time. And then you use the inverse flow of the driving system, and you can write it in this way. And now you see that if you use a reservoir state at the previous time, it is also a nonlinear function of the state of the input signal, which is the composition of this inverse flow and the function psi, which comes from generalized synchronization. And in this way, you can generate new additional nonlinear functions between the driving system and the output of the reservoir. And you can extend your set of basis functions, basically. And this idea has been proposed some years ago. And let me show you a simple example that this really works. Normally, people say you need a high-dimensional system as a reservoir. I'm not sure, because look at this. Here we have the following task. We have this famous Rössler attractor, chaotic system in 3D, and we have one variable that we can observe, the Z1 variable, which is the first variable. And let's say our task is cross-prediction of the other two variables, Z2 and Z3. And we want to do it now. We want to do it with a three-dimensional reservoir system, just three-dimensional, no 300. And this three-dimensional reservoir system is actually based on the Lorentz 63 model. If you take the Lorentz 63 model, you put here in front some time-scaling parameter to adjust timescales, and then here some of the variables, there is a U. And the U comes from, is the input signal. So the architecture of this reservoir system is similar to a Lorentz system, but with some input. So this can be used to solve this cross-prediction task. In particular, if you are willing to use previous values. And this is what I will show you now. So on the next graph, you will see prediction results where we used as for the formulation of the reservoir output, not only the variables of the reservoir variables at time t, but also with 100 past values. And if you do this, you see you can very well predict the dynamics of the two other variables of the Rössler system from the first one. Here you see true solution and predicted. You see they coincide quite well. This is the error signal. So this is an example where we use a three-dimensional reservoir, but actually it was higher dimensional because we also used the previous. So we have three variables in the reservoir system, but due to the fact that we used 100 values from the past each of them. Of course, we extended again the number of functions to be superimposed, and that's why it works. And this approach can, of course, also be applied to FO-state networks, for example. So this is a traditional FO-state network. Here, there is some input time series and the constant. This is fed into the reservoir, and then you compute here the output, for example, the desired quantity can be the future value, and in this way you can then close the loop. And if you use delayed input, it's basically the same architecture, but you use not only the value at time m here, but also a previous value. That's why it's written here delayed input, so that you extend the input signal to the reservoir. You can also use, as an alternative, you can use delayed reservoirs. In this case, and this is what I did in my example in the previous slide with the Western system, you can use delayed reservoirs. So the input signal is only this one, but the reservoir state is not at time m, but also the previous state as used as input. And then, of course, you can combine both. You can use delayed input and delayed reservoir states as input and study how this improves the prediction performance of the reservoir system. And to make a long story short, it can improve quite considerable the performance, but it does it only if you use partial state knowledge. In other words, what you see here is the following. For the Lorentz 63, if you have full state knowledge, this dimension here is the number of delayed reservoirs, so how many previous values from the reservoir states you are taking into account. And this dimension, vertical, is the delayed inputs, how many previous values of the input signal you used. And if you use, if you consider 0, 0, then you use only the current states. That's the conventional approach. If you use more, if you really go into the past, you see it getting blue. And blue means in this context bad, because the color code shows the performance deviation of this approach compared to the classical one. That's why it is 0 here. There's no difference. Of course, this is the classical case. You do not take into account values from the past. But if you do, things become worse. But if you do the same thing in a situation where you have partial state knowledge, only a univariate time series, for example, then you see it's getting red, and red is good in this case because it's you get a better performance. So again, there is a difference between the situation of full state knowledge and of partial state knowledge. But this is of course more important because in any practical application, you probably only have one time series or two, but not the full state. So in a sense, this is good news. But one really has to make sure that one distinguishes both cases. And here is the same. No, this is just again what I said. Okay, and the same situation for the Lorentz 96, the higher dimensional case. Again, it's not so strong here. It's only 10%, but basically the same result. And we also studied other systems. Now my last part, the prediction of spatial temporal time series. So far we considered only a Lorentz system and so on. The Lorentz 96 you could call spatial temporal if you want because it's this ring structure. But we are now looking at really spatial temporal systems given by PDEs, partial differential equations. And the famous example for demonstrating these methods is the Kuramoto-Shibashinsky model, which is shown here. A partial differential equation, you see here, fourth derivative in space. And it produces these dynamics, which is shown here in the top. So on the horizontal axis, it's again time, measured again in this Lyapunov times. And what is shown color-coded here is the variable u of this Kuramoto-Shibashinsky model. And it's a chaotic development. What you see here is the result of iterative prediction. And you see here the dashed line. This is where the errors become large because you see the difference between both of them here. It's practically 0, and suddenly we see the differences. So the diagonal of time here is about 10. So this was obtained here now. This is if you look in the literature, you will find 10 is a good value for this system. And how do we achieve it? With two ingredients or concept. One is using parallel reservoirs, which is not so new, and you can use it. I will show it in a moment. And then the second step, we use dimension reduction, which I will show you also. The diagonal time is, the prediction time is 10 diagonal times. Good. The problem, if you go step back a bit, in general, if you have a high-dimensional system, you would need very large reservoirs to do predictions. Let's go back for a moment to the Lawrence 96 model, and you see here the system dimension is increased here, 15 elements. You see here on the horizontal and the vertical axis the valid time. You see it goes down. For each of these cases, a full optimization of hyperparameters has been done. So there is a trend downward. The higher dimensional, the signal, the more difficult it is to predict it. Maybe not surprising. Here you see how the valid times, the optimized valid times, and optimized means using very carefully chosen hyperparameters, increases with the number of reservoir nodes. If you make your reservoir larger, this is this axis here, then of course the valid time increases. Here, this red one is for the Lawrence model. The Lawrence 96 is shown here in blue. It increases later or only for higher reservoirs, but still it does. And the green curve here is computed for the Kuramoto-Shibashinsky model, where the discretization of the PDE in space was with 128 nodes. And you see here you need at least 1,000 reservoir nodes before it slowly starts. And probably you should use 10,000 or 100,000 to get reasonable results. And just to remind you, in the example I showed you in the 2 slides before, we had a valid time of 10, so it was here. So this means for this axis, you really would have to go to extremely large reservoirs to get this result. That's the general problem, also calls the curse of dimensionality. And to overcome this problem, there are 2 ways at least. One is to use reservoirs, smaller reservoirs, instead of a large one, use many small reservoirs operating in space in parallel, next to each other. So this is illustrated here for the one-dimensional Kuramoto-Shibashinsky equation, which is here. And this is the full domain of the system, and we split it into 2 parts, simplest case, with some overlap here. Then we take this part here, pass it in a reservoir, do some prediction, and we do in parallel the same with the other part, reservoir prediction, and then you combine it again. The advantage is that these reservoirs, they see only part of the system, they see only less complex dynamics, not the full thing. And of course you would do that not only with 2, but you would use more. And if you do so, then you find the following. These are the best mean valid times for different numbers of parallel reservoirs. So this is one, only one big reservoir. This is the blue curve here. We increase again the reservoir size and we look how much the valid times, the ability to predict in the future is increasing. And you see, yes, increases here, but slowly. If we use 2, it's a bit better. But then if you use 4 reservoirs running in parallel, this is the green curve here. And you see it's increasing much more quickly, and then we use 8 and 16 and 32, the black one. And the black one already starts here, something 200 increasing. So using 32 reservoirs, small reservoirs, 200 only, is much better than using one big one. And this has been observed by many people, as I said, it's several years ago already. And now you may ask, okay, I need this overlap here. How should I use this? And it turns out there is an optimal size. Maybe it's not necessary to go into details, but you see, this is a number of reservoirs, so there's the size of the reservoir, the number of nodes, so the size of the reservoir. And this is here on this vertical axis is now the neighborhood length, so the amount of overlap here. And then you see that the best valid times are somewhere here, so there is an optimal neighborhood size. And this was one trick. Now comes the other one, linear dimensionality and reduction. Or dimensionality reduction, we did it linear. So what is the idea? We have here our dynamics, can be the full reservoir, but it can also be only a part. I'll come back to this. Then you see L here. L is a linear operation. In our case, we use PCA modes. And this provides a new representation of the dynamics. And then we use only part of this, the dominant modes. In this case, 75%, as you can imagine, 25 is already quite good. So we use only this part here. So we did some dimension reduction, feed it into a reservoir, predict the future value of the full representation, but in this latent space. And then we use the inverse operation to reconstruct the dynamics in our input space. And to restore the states. So this is the idea. And I will show you now, well, this works quite well because, at least for the Kuramoto-Shiloshinsky equation, if you look at the PCA modes, for example, you see the dominant modes are shown here, and the explained variance is shown here as a blue curve. So if this is 25%, for example, with 25% of the modes, you have already almost perfect description of the dynamics. The remaining modes are negligible. We also did this with the Fourier analysis and dominant modes, and it also works. Maybe not that well, but it's another way to do this dimension reduction, focusing on important Fourier modes. And now comes the interesting part. I mean, you can do this, you can think, well, I hope it works. And we found something which surprised us a bit. So what you see here is now the following. Again, this is the Kuramoto-Shiloshinsky model. We use now 32 parallel reservoirs. For each of the parallel reservoirs, we use this dimension reduction. And each of these reservoirs has this dimension, this number of nodes on the horizontal axis. And then you see here the valid time. And you see different curves in different colors. This is in orange, this one here, is for, if we use only 25% of the PCA modes, so we do a dimension reduction by a factor of 4. This curve here is 50%, and this is 75%. Now, if we use large networks, relatively large, 1,000 or more nodes for each reservoir, we have 32 running in parallel, but for each of them we use 1,000 nodes or more. Then we see what you expect. That if you use only 25%, for example, of your dominant modes, then the performance of the valid time is worse compared to the case with 100% or identity. So there, yeah, you have thrown away something in the dimension reduction step. Okay, what can you expect? But the interesting thing is now, if you go to small networks, below 1,000, you see this. And this means for small networks, using the dimension reduction even improves situation. The valley times with dimension reduction are higher than the valley times without dimension reduction. And this is something, of course, one has to study in more detail, but it's for me it was surprising, but I think it's also very good news because it shows, yes, you use the parallel approach, and then you use, in addition, you will have small networks already because you use the parallel approach, and then if you have the small networks, it even pays to use additional dimension reduction because this really improves again the situation. Okay, so I think this was, oops. This is now the same story with FFT. Same behavior. For larger networks, things become worse if we throw away a lot of the modes. But for small networks, we can even improve compared to the case without dimension reduction. Okay, and this is again in a different way. We show the relative improvement. Maybe we don't have to go into these details. The main message is that for small networks, you see these peaks here larger than 1. Larger than 1 means that the valid time with dimension reduction is better than the valid time without dimension reduction. Good, let me summarize. Generally, I would say reservoir computing can be characterized in saying that you use or we exploit the reproducible response from triple dynamical systems, can be recurrent networks, can be laser systems, can be many other systems, for some prediction, which can also be done iteratively. What? The training is in principle simple, it's fast, because you only have to solve a linear least squares problem, but there are additional hyperparameters, and they also have to be chosen carefully to get really good performance, and that makes it a bit more expensive again. It has been observed that incorporating delayed values improves prediction, and actually also makes it easier to find optimal hyperparameters. So we will talk about that, but that's another aspect. And but this is only really working in the case of what I call partial state knowledge. If you have only a univariate time series, if you have the full state, then it doesn't help much. Even sometimes it makes it even worse. And then I talked in the second part of the talk about spatial temporal dynamics and prediction of spatial temporal time series. And there are basically 2 ways to improve prediction or make it possible at all. Because if you would consider a 2 or 3 dimensional dynamical system, PDE system, it would be hopeless to use just a single conventional reservoir approach. You have to use this idea to use parallel reservoirs, and you can even improve the situation if you apply additional dimension reduction. And this is something we are currently studying and may help to cope also with the more complex dynamics, for example, the 2D or 3D cardiac dynamics we are interested in to describe. So let me also mention there is a focus issue in the German chaos on nonlinear dynamics of reservoir computing, which has been opened quite recently. So you're welcome to submit your work or look there for new papers appearing there. And I also would like to acknowledge again my collaborations, Luke Kellerman and Gerhard Welliker. I mentioned them already in the beginning, and also Hiromichi Suitami, with whom I'm discussing these topics. And then I would like to thank Stefan Lütter and all members of our research group, actually, who contributed in different ways, of course, to all this work. And I want to thank you for your attention. Thank you.
Questions? One question. My question is with respect to the optimization of the parameter inside the reservoir. How do you do that?
the parameters inside the reservoir. Yeah, these random matrices are just random matrices. And of course, you have to repeat this several times and to see what is the mean performance. I didn't say this. So these parameters are not really optimized in a systematic way. The other parameters, these hyperparameters, these 5 or 6 values, you can use a grid search in a 3, 4, 5, 6 dimensional parameter space, which is then very expensive. Or you can also use gradient descent methods in this hyperparameter space. But this is has also problems. I mean, you can do it, but if your error landscape or is complicated, then you may end up, of course, in the local minimum and all these issues. I don't know whether this answers your question.
So this reservoir completely has been around for, let's say, 20 years now, decades. And now it's kind of a hot topic. I guess this is because maybe the work of George Alton.
Yes, I think
prediction in the time series, but it was prediction of counting in time series, right?
Yes, I mean, it became popular mainly by work of Ott and his group.
Yeah.
Also, other people before did time series prediction. Actually, there's an old paper by Jäger who did it. But it was not so much noticed in the community of dynamical systems. Then the dynamical systems became interested because of connection to synchronization and dynamics and so on. Also, maybe because there is a general hype on machine learning. This is also, of course, contributing. I think at the moment I have the impression that it's mainly the people from physics, dynamical systems, who are interested in this, not so much the people from machine learning. But of course, the main hope is that this approach can be used for hardware implementations, or to implement this with hardware, which is fast and has low energy consumption. If all you can do on a digital computer, you can probably do better using other methods for machine learning. But there's a lot of work or a lot of activities now to test all kinds of hardware, spintronics, quantum computing, and so on, and to use this idea in a context where you implement it on hardware. And we will see how far this can go.
Have you tried, I mean, you work in cardiac heart dynamics. Have you implemented this approach to study the heart dynamics or not yet?
Well, I mean, of course, we are studying the spatial temporal dynamics, or the prediction of spatial temporal dynamics, and we also apply it to time series which were generated from cardiac heart dynamics in simulation. We also want to do it with measured data, but this is not so easy because the measured data are very, very noisy, they are very short, and if you want to do it with human data, it's also not so easy to measure them because you cannot extract the heart and measure it. You have to do it somehow inside. Yeah, but you really need spatial resolution. And then there's also a lot of activity now to use ultrasound movies, 4D. But the ultrasound signal quality is of course quite low. But we have the goal to apply it there. But we are now in the state to develop the programs and the skills to use them. You see.
Further questions. So if not, we thank again.